semicolon though. Z is a function of x and y, right?
Mhm.
This is coming from 14.5. X is a function of t. X is a function of t. X is 1 over t squared. Y equals, y is also a function of t. Cosine of 4t. Everything in section 14.5, you'll notice, is usually find the rate of change. It is rate of change. But the rate of change of this function, z, with respect to t. Some problems have another variable s in there, so they might have to find the rate of change with respect to s. But our problem, this is what we're trying to find. Find dz dt. So we look there, and we're like, what the heck, how do you do this? Because z is a function of what? X and y, does everyone agree? Z is a function of x and y, we gotta find the rate of change of z with respect to t. And Calc 3, you just say, I just need chain rule. That's all I need. So I need to go back to Calc 1 days so we can figure out the formula for this. What was chain rule then? Well, I'm not talking about an f prime, like there's a better way to write it. Do you recall I could think of chain rule as derivative of y with respect to u times derivative of u with respect to x? Did you know that? That's exactly how I could think of chain rule in Calc 1. I know it's in another notation with the f prime of g of x times g prime of x. That's another way they write chain rule. But this is one popular way that chain rule is presented in Calculus 1. That's what this will be. But we just need two of them because z is a function of how many variables? Two. So I'm going to set this up. Ready? You'll find this real easy. I'm going to set one up for the x's. I'll put some quotation. I need one for the x's. So I'm going to do dz here, dt, and I'll put a plus, and I'm going to do another one for the y's. dz, dt. Now these are partial derivatives. So I think what I'll do is I'll just take that d and make it a delta. I hope that doesn't bug anybody. Remember, the deltas look just like d's. I don't care if you use d's. But this is with respect to the what? dz dt. dz dt, I need one for the x's, and I need one for the y's. That's it. I'll just make this look like they're deltas there. So I did dy dy, dx dx, whoops, that's an x. Look, dx dx, dy dy, just like I had that chain rule there. When I wrote dy du, du dx. This is chain rule. We just got four things we gotta compute. We just got four things we gotta compute. So I'll put that down, everyone. Like, and z is a function of like x and y. Now what's dz dt gonna be? Delta z, delta x, delta x, delta t, plus delta z, delta y, delta y, delta. Hey, another note. What if this had another variable like j in here? Say z was a function of y, x, and j. I would just add another what?
D.
Now we're going to z dt, and then in these corners I would have put the dj's. All right, now help me get this. What's the partial of z with respect to x? Oh, tough one. We're starting with a tough one. What's the partial of that with respect to x? These are partial derivatives. Man, you are good. Is someone okay with that? They get y squared e to the xy. What's the partial of x with respect to t? Like, well, x is only a variable function of t, so just get the derivative of x with respect to t. I don't have to put deltas here. What's the derivative of x with respect to t? That's t to a negative 2. So it would be what? Negative 2 t to the negative 3? What's another way to write that? I'm going to write it like that. Negative 2 over t cubed. Nice. What's partial root of z with respect to y? Crap. I'm getting it ready. You all spot it? Look how much room I'm leaving. I didn't need much room here. I think this is the first time you and I are doing a partial derivative together where we need product rule. Why do I need product rule? Because there's a y here and there's a y there. Does everyone see that? So I'm going to think of this like first times derivative of the second plus the second times derivative of the first. All right, here I go. First times derivative of the second. And x times e dxy plus the second e to the xy times derivative of the first, which is a 1. Oh, cool, I didn't need so much room. Was everyone okay with that? I just did product rule. You don't use it too often with partial derivatives, but we needed it there. Right? Every once in a while you need a quotient rule. We haven't needed that yet. Oh, what's your y? Spent the t, just remember chain rule. -4 sine of what? 14? Is everyone okay with that? Hey, let's apply this to 2 problems and we'll be done. You have that 14.4 to 14.6? I'm going to hit this on the light so you all can read it. I have to write it all out. Let's look at, how about we're going to do number 9, then we'll do number 11. Oh, these will be quick. We'll be done. Number 9, number 11. This is just on practice. What I'm going to write on the board is this equation I see in number 9. It says k equals 1/2 mc squared. Good? You can't use this?
Oh, yeah, sure.
That way everyone can read it. So we're talking about number 9. Think of the kinetic energy of an object with mass m moving at the speed v is given by k equal to 1/2 mv squared. At a given instant, the rocket with mass of 100 kilograms traveling 120 meters per second. The mass of the rocket is decreasing at a rate of 3 kilograms per second. Be careful that when they said decreasing. So you can help me do that when we plug it into the math, into the formula. And it's increasing at the rate of 70 meters per second squared. The rocket is accelerating forward. The rate of change of kinetic energy is closest to. So when we're finding rate of change with respect to time, when you hear that in this course, you're thinking chain rule. Because I need rate of change with respect to time, and this doesn't have time, right? So k is a function of how many variables? 2. So this is what we're looking for. dk dt. But I need one for the what? dk dt plus dk and dt. And I know if you say, gosh, how do I know when to use this chain rule problem? Or how do I know when to use chain rule in Calc 3? You see the word problem, it's when you're trying to find the rate of change with respect to time in these application problems, which we're trying to do, right? So what variable goes here? And how about here? And what's the 4 things we do? We get all these. A couple of numbers are given in the word problem. Like I see this 120. What is that? Traveling at 120 meters per second. What would that be? Rate of change of what? Yep. Rate of change of velocity with respect to time. Does everyone agree? See it right there? That's velocity, right? And they said, or that's the change in the rate of, is increasing at a rate of 70 meters per second. But this right here At a given instant, a rock with a mass 100 kilograms is traveling at 120 meters per second. So we'll figure all these out. But before we plug those numbers in, can you get these partial derivatives? So this is really delta K, delta M. And this is really delta K, delta V. These are partial derivatives. What's that partial derivative with respect to M? Ooh, 2 times a half is 1. V squared, right? And what are we plugging in there again? The velocity was what?
120.
120 squared. What was the rate of change of the mass? The mass of the rocket is decreasing at what rate?
3 kilo.
3 kilograms per second. Was everyone okay with this partial derivative? So I'm doing the derivative of this with respect to M.
The M should just go away.
And the M goes away, but what has to stick? Right? This is constant. We're thinking, I took this as a constant, and so this should just be that V squared was a constant. True, right? Let me do this again. If this is a constant, and that's a constant, the M should just go away like you said, and I should have the V squared, but what's right underneath it? A 2. Very good. Is everyone okay with this partial derivative? It can be tricky sometimes, but you're right. You're exactly right. You're like, just that M disappears. This is like 5x, the derivative is 5. Or 10x, and the derivative is 10. So we get that, and then we're going to plug in a number eventually. The velocity that they use. This number was given in the problem. What was it? Excellent. Did you hear this? He said negative. The mass of the rocket is decreasing. I don't want that decrease to ever get you, throw you off. Be careful with that. Be careful when they say decreasing, because that means the rate's going to be negative. What's partial derivative of K with respect to V? MV. 2 times a half is 1 MV. And then that's just acceleration, right? Rate of change of velocity with respect to time. What was the acceleration they were saying?
70.
70. Now, what gets plugged in here? They had to give me these. That was the one. Was that 120?
Yeah.
Then 70, and then the MV. What's the M and the V?
1000 kg.
M was, mass was
100
kilograms, and
102.
now you don't have to do all this math right now, but while you calculate, you get the answer, right? And they give the units. This is chain rule. Well, I just want, once you have this copy, I just want to do one more from the sheet. I think you'll find it a lot quicker. Sometimes you have to find partial derivatives, right? Good job with that. Last problem. Sometimes, it's not so bad. Let's do number 11. Maybe I'll enlarge this. Let's see. Yes, better. All right, last problem, number 11. Suppose the speed of sound is in meters per second. Is a function S equals F of P and T. P is the pressure. T is temperature. They give you all these numbers. Find the rate at which the speed of sound is changing. I need the rate of change with respect to time. I need the rate of change of S with respect to lowercase t. Now S was a function of how many variables?
2.
P and what?
T.
So in the hardest part to chain rule, I think, would just be the setup. Do you agree? I'll hit the lights up, and then I'll put them back on, just so people can see this. S was a function of uppercase P and uppercase T. Somebody do ds, dt. Do it again. ds, dt. This will be, there's 2 p's, and this will be my dt. pdp and TDT. And please feel free to make these deltas as if they're partial derivatives. The deltas look like these. So we got 4 things to get. Well, what is the rate of change of F with respect to P? Well, this is weird, Aaron, because I see this. They give me a number right there. But it has an F. Well, isn't FS?
Mm-hmm.
So it's the same thing, and when I get to use that same number there. S was the function. So I can put that number right there, that 4 goes here, right? That's given to me. And I see this number is given too. What's that number? 10. But how do I get these? What's the derivative of P with respect to T? And you're like, gosh, this is a lot easier than the last one. What's that derivative? Just AT?
Mm-hmm.
And what do I gotta plug in? What was the time they asked for? So I'll drop a line. What do I gotta plug in here?
3.
At
3.
T equal to 3? Okay, so we'll plug in that 3 there. And then what's the derivative partial derivative temperature with respect to time?
30 minus 50.
So this derivative is just what? Negative 5?
5, yeah.
So we put negative 5. So our final answer is 4 times 24 plus negative 50. What's 96 minus 50?
46.
And what are the units for this problem? We're going to put it instead in meters per second per hour. So I'll write that. M per S per hour. And you all, great job today. Thanks. Got the 5.